You sit down, open paper 2, spot a kinematics question, and immediately plug in your numbers. You move on feeling absolutely brilliant, completely unaware you just threw away a massive chunk of marks in the first 3 seconds. Why? Because of one tiny, almost invisible terminology mistake. Today, in this explainer, we are entirely skipping the fluff. We're instantly exposing the motion trap that ruins grades before students even realize what hit them.
15%. Just let that number sink in for a second. The core topic we're unpacking today, equations of motion, distance, displacement, speed, velocity, and acceleration, literally accounts for about 15% of the total marks in physics paper 2. We aren't talking about some obscure subtopic here. This is a foundational pillar. If you mess this up, you're instantly risking a massive grade boundary drop. The stakes are just incredibly high. And Cambridge examiners, they know exactly how to test if you actually understand the physics or if you're just blindly memorizing equations.
And that leads us right into the silent killer that trips up thousands of students every single year: confusing distance and displacement. Now, I know it sounds so basic, right? Like, I learned this years ago, but under the crushing pressure of an exam, casually swapping these two terms instantly crashes your calculation. You literally end up applying the right formula to a completely wrong physical reality. And suddenly, your exam timing is totally ruined because you're chasing a mathematical dead end. This brilliantly illustrates exactly why ordinary, surface-level revision just completely fails. Look at the fundamental difference here. Distance is a scalar quantity, right? It's just the total path taken. But displacement? It's a vector. It is the straight-line distance from the origin in a specific direction. The 9702 syllabus doesn't just want you to recite definitions. The academic benchmarks actually require logical, structured reasoning. They heavily prioritize analytical depth over superficial breadth. If you don't treat these terms as entirely different analytical tools, well, your equations of motion will literally just fall apart. And this cascades directly into our next trap. See, speed is the rate of change of distance, but velocity is the rate of change of displacement. If you use a scalar approach in a vector context, like, say, ignoring a change in direction when calculating velocity, you are fundamentally taking the wrong approach. And in Cambridge exams, using the wrong approach for the context, that cascades into massive, unrecoverable mark losses. Now, what's really eye-opening is that we pulled these 3 warnings straight from the Cambridge Principal Examiner reports. This is the harsh reality of exactly where students bleed marks. Number 1, using the wrong approach for the specific context of the question. Number 2, poor format and presentation of calculations. And number 3, providing answers that are generic and just not specific to the data given. It is simply not enough to just know the physics. You have to present it exactly how the examiner expects to see it. Which brings us to a really critical turning point. In a moment, I'll show you the exact examiner clue that changes the answer completely. But first, you need the procedural framework that makes that clue completely obvious to spot. If you skip this framework, you're basically going to be playing a guessing game with a mark scheme for the rest of your revision. So here is your ultimate procedural framework to systematically process complex exam questions without ever losing your way. Step 1. Extract the relevant data from the texts, graphs, or tables. Step 2. Select the correct analytical framework, meaning pick the right principles and equations based on whether you're dealing with scalars or vectors. Step 3. Execute the analysis with perfectly clear notation. And finally, Step 4. Verify your results and present them in the appropriate format with the correct terminology. This standardized sequence, it's exactly what high-scoring candidates do automatically. Let's see how this actually builds into the specific analytical sequence required to craft a written answer that perfectly mirrors the mark scheme. First, you state the core concept. Then, you link it to the specific evidence or data you extracted from the question. Next, you apply your scientific reasoning to connect those two things. And finally, and honestly, this is absolutely crucial, you package it using the exact examiner wording expected for that topic. It's a precise, 4-step recipe for top band marks. But what if you make a calculation error? Well, listen to this direct warning from a principal examiner. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. This is the absolutely vital method mark strategy. Showing your clear step-by-step working is literally the ultimate safety net for your grade. Examiners actively want to give you marks for your process, even if your calculator finger slipped at the very last second. So never ever just write down a final number. Okay, let's put this into practice right now with an interactive challenge. I want you to spot the error in the scenario we're looking at. Imagine a car traveling at an initial velocity. It hits the brakes and comes to a complete stop. A student is trying to calculate the time it takes to stop using the equations of motion. Take a mental pause right here and predict exactly where the most common mistake is going to happen. All right, here is the crucial breaking point. The student used the right equation, v equals u plus at, but they completely forgot that because the car is decelerating, the acceleration vector a must be negative. This is a highly typical, totally flawed student answer that demonstrates exactly how contextual application just falls apart without systematic processing. They treated a vector like a scalar, and the whole calculation collapsed.
Let's break down the stark contrast between these two approaches. On the left, we've got the descriptive, mark-losing attempt. Missed vector signs, a messy jumble of numbers, and zero clear working shown. Then on the right, we have the top band success. The clear vector direction is indicated, step-by-step working is perfectly formatted, and the answer is tied specifically to the context. This correct approach on the right is exactly what Cambridge examiners are desperately looking for when they grade your paper.
When you faithfully apply our 4-step framework, those previously hidden examiner clues, like the word decelerates or returns to its starting point, they suddenly become incredibly obvious. You naturally extract them in step 1, which guarantees you select the right vector notation in step 2. Your concept perfectly matches the examiner's expected wording, making it incredibly easy for them to just award you full marks.
But here is a terrifying thought. What if you know the physics perfectly? Like, what if you apply the framework flawlessly, your math is pristine, your presentation is gorgeous, yet you still score 0 marks for the question? How is that even possible?
Well, it happens because of the diagnostic cliffhanger we're ending on today, the command word trap. See, the higher order assessment objectives in the 9702 syllabus demand totally different things based on one single verb at the start of the question. If the question says evaluate, and you only describe, your perfect physics knowledge is essentially worthless because you answered the wrong prompt. Command words dictate your mark band, and understanding them is the absolute mandatory next step to secure your grade. To ensure you don't fall into that exact trap, and to really master the hidden language of Cambridge mark schemes, subscribe to our YouTube channel, Ace the Exams, at AC Exams IGCSE, to excel in your Cambridge examinations. Our next explainer, diving deeply into those critical command words, is your essential next step. Until then, ask yourself, are you just memorizing equations, or are you actually answering the question the examiner is asking? See you next time.